So, as we just defined our system, let us first draw what we mean by these layers. So, as we just said that let us suppose that the system is composed of some layers, or we can think that there are arbitrarily that along z axis there are some layers. So, let me actually draw the z axis like this so that you get a feeling of the 3D version. So, this is the z axis. Now, suppose we are talking about flux across this particular layer which I have denoted at the middle. So, this particular layer, and let us say the position along z axis it is around some origin. Let's say I am calling it as z0. It will not be 0, some position along z0. So, I want to calculate the net flux across this surface. Now, in order to do that, we can do two ways. So, there are some molecules which are coming, or particles which are coming from vertically from top, and some molecules which are coming vertically from bottom. Now, what do you mean by these layers then? So, these layers are something which are actually lying at distance which is equal to the mean free path between mean free path of the molecules, which means actually this makes sense because if we want to calculate the flux, we are saying that from this layer and to this layer the molecules are coming without any collision, and that basically connects us to the definition of mean free path, because by definition mean free path is nothing but the path a molecule makes because between two successive collisions. Because if you have a collision in between these two layers, the trajectory may get drifted and we won't be able to calculate it nicely. So, the assumption here is that, not the assumption, we are actually considering the layers at basically distances which are at the mean free path distance of the system. Now, what is the mean free path? Now, mean free path you can easily calculate. See, if the velocity is suppose v, and you can easily say that this average velocity times delta t, which is nothing but the average velocity divided by the number of collisions for if the collisions are between a same type of molecules, and that we actually define by mean free path in kinetic theory of gases. But here we have a conceptual problem because this does not have any orientation inherent to it. Meaning, if you remember correctly, for the generalized orientation, we said that the cylinder is actually in a slanted position. So, what we have to do, we have to actually calculate the vertical distance between these two layers. So, what I am trying to say here, suppose these are the distance between these two layers, and all I know is basically this is the lambda, but what I want to calculate is the vertical distance, which is nothing but, in our definition, it is lambda cos theta, because this was the theta. So, then again I have to think about that there is an average of these thetas. So, I have to again calculate the average of that mean free path. So, the vertical mean free path, or the vertical distance between these layers, if I just call it as a vertical distance or the vertical mean free path, vertical mean free path, that will be nothing but the average of this lambda cos theta. Now, average over what? Average over basically all possible distribution. Now, when you take the distribution, what we have derived so far is a quantity, if you remember, of this entire thing, the z thing. But if we just say that this up to this point, this quantity, whatever we are just writing, so this, if I write it as say some j which is dependent on v, theta and phi, and then we had to multiply it by v square sin theta d theta d phi, and if we integrate all this thing, then we get the j z value. So, if we define it in that way, So this is nothing but this mean free path also has to be weighted by the flux, because flux is nothing but again probability distribution. So we are basically integrating it with respect to theta, phi and v, and with all this integration d theta, d phi, dv with v square and all this term, but that I am suppose writing it as d tau, and divided it by, if the zz is not a normalized probability distribution, we have to also divide it by the integration over zz. Now this is a rather simple integration, because as you can see, all we have to do is the theta part integration. But again, we have to be very careful, because within zz we know that what was zz, remember that we had a sine theta, d theta and cos theta, so that we integrated. But now actually we are taking another cos theta, because you are taking the projection for lambda. So all other things like d phi and dv part we don't need to consider, because we have the same thing in the numerator and the denominator, then they will cancel out. So lambda by definition is not dependent on theta, that's a constant that is coming directly from our mean free path, but in this case it is the angular mean free path. And then all we are left with is basically an integration after we integrate out the v and phi part. So we will have a cos theta, and remember it will be basically cosine square theta sine theta d theta divided by, for the j part it will be basically cos theta sine theta d theta, and this integration is again from 0 to pi by 2 for the reason we just discussed. Now how to evaluate this integration? It's also very easy, and if you follow these things, so this integration will be nothing but you can use actually the tricks. You can write actually sine theta d theta in terms of say d of cos theta with a minus sign, because d of cos theta is minus of sine theta. So ultimately it will be a cos cube theta divided by 3 evaluated between 0 and pi by 2, and the denominator will be the same. We have already integrated that part out. It will be cos square theta for the same reason. Sine theta d theta you take as minus cos theta, or you just write cos theta d theta as sine theta, sine d of sine theta, either way is fine. And then it will be evaluated like this, and there was a lambda. So what we'll get ultimately is basically this value will be 2/3. You can easily check it. So it will be nothing but of 2/3 of lambda. So what we learned is that this distance, if this plane is located at z0, the middle plane, this is located at z0 plus 2 lambda, 2/3 lambda, and this is located as z0 minus 2/3 lambda. So now all we are saying is that we have to calculate the net flux across this surface which is at the center, which is lying at the middle, which is basically at z0, for the molecules which are coming from top from a layer which is lying at z0 plus 2/3 of lambda, and from molecules which are going up, which are coming from a layer which is lying at a distance z0 minus 2/3 lambda. So now how will I calculate it? It's also very easy. We'll just use just a phenomenological notation, in the sense that we are saying that okay, let us calculate the net flux, and this net flux will be like net positive flux which is going in the plus z direction, and also I have to subtract the net negative flux. Now remember that the positive flux which is going in the upward direction is coming from the lower layer. So these molecules are going upward from this layer. So if I call it as a say layer number 1, this is 2 and this is 3. So it is coming from layer number 3, and the downward flux is coming from layer number 2. So you have to be very careful. So for the positive flux, it will be nothing but we will use the definition. It is 1/4 average velocity. Now J, or the flux, which is the positive flux coming from the bottom layer, which means actually it is nothing but this quantity n star. And now before we write something else, let us first say that I write it as Jz is 1/4 n star into V average. But suppose this is basically the Jz, let me write it once again, 1/4 V average into n star. So that basically tells you what are the number of molecules which are moving in the upward or some direction. Now suppose each molecule is carrying something. What is this something? Suppose each molecule is carrying some momentum, or each particle is carrying some momentum. So the flux will have also instead of the number of molecules per unit time per unit second, it will be the momentum transferred per unit time per unit square area. So which means I have to multiply by some quantity, and this quantity will differ from one problem to another problem. Meaning when we are talking about, say, viscosity, not viscosity, let's say diffusion. Viscosity is a little bit complicated because it will be the x component of velocity. We will discuss about it. Suppose we are talking about the diffusion simply. So then it is simple. So it is just the number of particles itself. It's a concentration gradient. So Q is doesn't make sense. But if it is a heat transfer equation, then actually the Q is basically the amount of heat carried by each particle per unit area per unit time. So then the Q, the dimension of the Q will be the dimension of heat, which is dimension of energy. Something will associate with that. And so in this case, we just leave it as n star into Q, and that quantity is changing. Now in order to calculate the net flux, we have to now calculate what is the value of this n star Q at for positive Z. Again, it is coming from bottom. So it means actually what is the value of n star Q at Z0 minus 2/3 lambda minus what is the value of this n star Q at Z0 plus 2/3 lambda. Now the textbooks we recommended for you, some textbook actually write this quantity n star into Q as rho suffix Q, but we are not using that notation because rho itself is used in many places as density, so we do not use that. So we'll just keep it as n star into Q. Now what you see here is that now that I do not know because it will depend on the gradient of that quantity. Which quantity? Q. Now n star is a density, and if you remember that there could be a density gradient plus there could be a gradient of a particular this property itself, the Q itself, and the gradient is along z axis. That's why the flow is happening. If the gradient is 0, so these two quantities will be identical, and then it will be just the same. So there will be no net flow. So now let us first define what will be this gradient. So what we are asking this question, what is the value of this n star into Q at Z0 plus 2/3 lambda or minus 2/3 lambda. Now we can say that okay, fine, let us say this gradient, the way it is changing in the positive x axis, positive z axis, sorry, this gradient or this quantity which is n star Q is changing along z linearly. So if it changes linearly, then it's a very simple equation. It is nothing but y equal to mx minus c, mx plus c, where actually m itself is a negative quantity because the slope is negative. So that way you can say that okay, fine, so I can say that it is nothing but the intercept. The intercept means at its value at z0 minus, for plus actually will have a minus because the gradient is changing in the positive direction, but since we have already taken that into account because we are considering the flux coming from bottom minus flux coming from top, so in that sense we can write it as this is nothing but the rate of change, and the rate of change is nothing but the slope or the gradient along z And now if you have a gradient, so basically suppose this is the z0 value, and this is at some point I want what is the value here. So what I have to do is that I have to take this gradient or the slope, which itself is a negative along z, and multiply it by where I am taking this value, right? So in this case it is nothing but evaluated at a distance which is 2/3 lambda away from that. So this will be the value, and then we can actually use another bracket maybe, or we can just leave it like that. So this is for plus and this is for minus. So again, the positive or negative sign is already inherent here. So we can actually go back and write the expression for our quantity, which is z, or the flux along net flux along z axis. So it will be 1/4 average velocity, and then first the net upward motion, or net upward flux, sorry. So it will be n star q evaluated at z0, and there was a minus sign, remember, because upward is coming from the lower bottom layer. So I have to consider minus 2/3 lambda into this gradient del of n star q del z, minus I have to subtract the net downward flux, which is nothing but n star q at z0, plus it will now have a plus because it is coming from the top layer. So it will be plus 2/3 lambda into the same quantity, which is del nz, sorry, del n star q del z. So as you can see, this constant term cancels out, and all will be left with. So you can see with this is minus 2/3 lambda, it is plus 2/3 lambda with a minus sign here. So it will be minus of 4/3 of lambda. So this 4 and 4, this 4 will get cancelled. So ultimately we will get minus 1/3 V average lambda times the gradient of this quantity del n star q del z, and this will be the equation for the net flux. Now you can see, now this is a very generalized equation. So what we did, let me again summarize. We just defined the quantity flux, and we defined it is the quantity which is being transported per unit area per unit time. So in order to define that, we just considered a surface, arbitrary surface located in our bulk system, bulk macroscopic system. But we gave a molecular picture, how basically, let us just calculate first the number of molecules, because it is the molecules which are carrying that property. It may be momentum, it may be heat, it may be something else. It may be the number of molecules itself. In that case, it's just the equation for diffusion. So then in that case, Q will be just 1. There's no extra quantity. Now we said that phenomenologically, the Poiseuille's law was nothing but that if we just remember the first slide we wrote, so that was nothing but some constant and multiplied by the gradient of that quantity. In Poiseuille's equation, it was a gradient of pressure, and we wrote it as del P del Z. So in this case, actually we can write it something like this. So gradient of that particular quantity along z axis. Now we see very interesting thing. What we see here, if we compare these two equations, we can actually get expression for this constant. And this constant, as I said, is basically nothing but 1/3 V average into mean free path. So that we'll see actually what are the consequences of this constant. So this is known as this constant will be the coefficient of that particular process. For example, if you talk about say viscosity, this will be the coefficient of viscosity in that case, but it will depend on what quantity we are talking about, what is the Q in that case, and how that derivative we can take out. So that will go through in detail. But before that, let us just try to understand what we just learned, and then or try to basically recapitulate what we just discussed. So we first talked about these layers, that there is a particular layer, and across that layer some flux, I mean we are going to calculate some flux, and then we considered that at a particular angle the molecules are coming and hitting this surface, but then we considered all possible distributions of this surface, but only from one side, because we are considering the flux along a particular direction. So say net downward flux or net upward flux, something like that. And for that actually we took the integration for the azimuthal angle, the theta, to be 0 to pi by 2, and then we considered also Maxwell-Boltzmann distribution, but we actually cleverly said that I will take the distribution function divided with by 4 pi v square, because Maxwell-Boltzmann distribution was already integrated as over theta and phi, but we don't want to integrate it. We want to actually use the Maxwell-Boltzmann distribution before the integration happen, going from velocity distribution to speed distribution. At that connection where I have the distribution of speeds, but it is still an angle dependent, because in our derivation we saw that there is a velocity distribution, and that we cleverly introduced in used the Maxwell-Boltzmann distribution, as well as the fact that we have to integrate over all these possible angles. And when you do that, then we figure out that we get a very simple expression in terms of the average velocity, and it is nothing but 1/4 of the 1/4 times the density times average velocity, but this is just the number of particles or number of molecules which are moving. If we are interested in the flux of a certain quantity that is carried by the molecule, so then you have to also multiply by the quantity itself, so carried by each molecule. And then we said that fine, it is basically a flux along a particular surface, but then you have to consider the net flux along the surface, and then since our problem is we have kept it very simple, one dimensional, along the choice of axis was z axis, along z axis. So we said that let us consider a layer along z axis across which we want to calculate this flux, and then we said that what are the other layers that we have to consider. So then we said molecules which are coming from immediately above and immediately below layer, that we are considering. But then we had a problem in defining what is the location of those layers which are lying above and below. So by definition, this is basically within the mean free path of the molecules. But then the way we define the problem, that the molecule can actually come at an arbitrary angle. For that, actually, if the mean free path is lambda, then the vertical angle will be lambda into cos theta, and then we again took the average of this mean free path, and we figured out that it will be basically 2/3 of lambda, that is the mean free path. So the layers are lying actually above 2/3 lambda and below 2/3 lambda, something like that, and the above layer corresponds to the downward flux and the below layer corresponds to the net upward flux. And then what we said is that we wanted to calculate the net upward flux, which is the flux due to the bottom layer minus flux due to the top layer, and we connected that quantity with the gradient, and we assumed a very simple gradient relationship in the sense that we said that the gradient is actually varying linearly, which may not be the case, which might have a very complicated variation. And then this gradient, if it varies linearly, so then we can actually just use a linear equation, and then we inserted that thing, and we showed that now the flux can be directly connected to the gradient of that quantity times mean free path times the average velocity. Now we'll stop here, and now we'll build upon on this particular topic, and we'll discuss about specific cases, like what will be the expression for heat transfer, what will be the expression for momentum transfer, what will be the expression for say just the transfer of molecules, which is diffusion, and we'll consider all this physical process. Again, these are all developed phenomenologically. And before you go through all these topics, I'll advise you that you go back and read the textbooks which are recommended to you, or you can actually go back and see my YouTube video lectures for the earlier course, where I actually derived the Maxwell-Boltzmann distribution from the very first principle, distribution of velocities. Then you will have an idea about this velocity distribution, how basically from speed distribution we get the velocity distribution. Now, before I conclude this part, I will just make few remarks. So here, during this entire derivation, we made some explicit assumptions, in the sense that we said, first of all, these molecules are still kind of rigid spheres, just like Maxwell-Boltzmann distribution we applied, and without any intermolecular interaction. So that's definitely an assumption, and that's why all these derivations which we did will hold true for gaseous system, where the attractions or repulsion, gas in a very dilute condition, of course, will be very minimal, not in condensed phase, because in that case the intermolecular forces will be very high. Number two is that we said that the molecules have actually equal speed, which is something like equal average velocity. In reality, it don't be true, although we took actually Maxwell-Boltzmann distribution of speed, but then you can think that the mean free path will be very different for each molecule. And we took the average, and then we took a mean free path for something, and then we took the average. So it's not a very rigorous derivation in that sense. And number three is we also assumed that it is basically isotropic in nature, and there is no angular variation. So isotropic angular distribution, in the sense that along the theta and phi, we just did not say that there is any gradient. So gradient is acting only along z. So it's a linear, it's basically gradient varying only along one dimension. So the entire problem is kind of one dimensional, although we are saying a three-dimensional, it's a three-dimensional system, but the gradient always happens in the one direction. That's why the flow, either heat flow or diffusion, whatever it is, mass flow in case of diffusion, that flow also happens in one direction. But in reality, you might have a gradient which also happen varying angularly. So then you have diffusion probably over a particular solid angle. And so this is the real life examples, but real life situations or scenarios, but we are not discussing those situations. We are making our analysis very simple. And the fourth thing is that the collision, each collision results in equilibrium. Equilibrium of what? It is equilibrium with respect to interchange of the property being transferred. Now this is a very important thing. What we said is that there is a mean free path of the molecules, and they are coming from the above layer, but then actually the molecules are also colliding, because mean free path is directly connected to the collision, because it is the path between two collisional events. And during the collision, the property also should change. But we are actually assuming the whatever collisions is happening, the collisions are happening in such a large number that those collisions are actually setting the system again in the equilibrium. So the explicitly, although each collision is changing, for example, a molecule was moving this direction and it collides with another molecule, and its direction and the magnitude of the momentum can of course can change, or not also will change. But we are saying that for a large number of molecules or a large ensemble of molecules or particles, it doesn't matter, because everything gets averaged out, and even with the collisions, the equilibrium is always maintained, or even immediately after the collision, the equilibrium is established. So these are the assumptions we made here, and those assumptions actually make this analysis very simple, because all we want to do is to understand the physics behind the transport phenomena in a very simple way. And again, at the very beginning we said that for a right way of doing it is that you have to consider the angular distribution, you have to consider the proper gradient, these are all vector quantities, although we are dealing with these as if they are scalar quantities, so which are not correct. But as long as we assume that it is a one-dimensional problem, it is perfectly fine, because if you just analyze properties of a vector along a particular direction, so it's just a scalar, so because there is no other component. So we'll just stop here, and in the next part we'll introduce you to the particular problems like mass flow or heat flow, which are connected to basically diffusion and heat transfer.